Understanding mechanical creep in semiconductor packaging. Introduction. Mechanical creep is a time-dependent deformation phenomenon observed in materials subjected to sustained mechanical loading at elevated temperatures. In semiconductor packaging, where devices are exposed to mechanical stresses and thermal cycling during operation, understanding mechanical creep is crucial for predicting long-term reliability and ensuring the durability of electronic components. This overview delves into the concept of mechanical creep, explores its mechanisms, factors influencing creep behavior, and its implications for semiconductor packaging. Definition and mechanisms of mechanical creep. Mechanical creep refers to the gradual and irreversible deformation of materials over time when subjected to constant or sustained mechanical loading at elevated temperatures. Creep deformation occurs through several mechanisms. Dislocation creep. Dislocation motion within crystalline materials under applied stress results in creep deformation, where dislocations climb over obstacles and rearrange lattice planes. Grain boundary sliding. At elevated temperatures, grain boundaries become mobile, facilitating grain boundary sliding, where grains deform by sliding past each other, leading to macroscopic deformation. Diffusional creep. Diffusion of atoms through lattice defects, such as vacancies or grain boundaries, promotes creep deformation by allowing atoms to rearrange and redistribute, reducing local stresses. Coble creep. Coble creep occurs in fine-grained materials, where grain boundary diffusion dominates deformation, leading to grain boundary sliding and grain boundary migration. Factors influencing mechanical creep. Several factors influence mechanical creep behavior in semiconductor packaging materials. Temperature. Creep rates increase exponentially with temperature, as higher temperatures enhance atomic mobility and promote creep mechanisms, such as dislocation glide, grain boundary sliding, and diffusional flow. Stress level. Creep rates are directly proportional to applied stress, as higher stress levels lead to increased dislocation motion, grain boundary sliding, and deformation rates, accelerating creep deformation. Material microstructure. Material microstructure, including grain size, grain orientation, and grain boundary characteristics, influences creep behavior by affecting dislocation mobility, grain boundary sliding, and diffusional processes. Environmental conditions. Environmental factors, such as humidity, atmospheric gases, and chemical exposure, can accelerate creep deformation by promoting material degradation, embrittlement, or grain boundary diffusion. Creep mechanisms. Creep behavior varies depending on the dominant creep mechanism, such as dislocation creep, grain boundary sliding, or diffusional creep, with each mechanism exhibiting distinct deformation characteristics and deformation rates. Time and load history. Creep deformation accumulates over time under sustained loading conditions, with creep rates influenced by loading history, temperature cycling, and thermal aging effects. Implications for semiconductor packaging. Mechanical creep has significant implications for semiconductor packaging, affecting reliability, durability, and long-term performance. Package deformation. Creep deformation can lead to dimensional changes, warpage, or distortion in semiconductor packages, compromising mechanical integrity, electrical connectivity, and device functionality. Interconnect reliability. Creep-induced stress relaxation in solder joints, interconnects, and bonding interfaces can lead to joint softening, creep deformation, and eventual failure, impacting package reliability and interconnect integrity. Dielectric integrity. Creep deformation in dielectric materials, such as encapsulants, mold compounds, or underfill materials, can lead to delamination, cracking, or void formation, compromising dielectric integrity and package reliability. Thermal management. Creep deformation in thermal interface materials, TIMs, heat sinks, or heat spreaders can affect thermal contact resistance, thermal conductivity, and heat dissipation efficiency, influencing package thermal management and device temperature control. Reliability prediction. Understanding creep behavior is essential for predicting long-term reliability, estimating service life, and assessing the durability of semiconductor packages under sustained mechanical loading and elevated temperatures.